Hello, welcome to our channel for probability and statistics. In this video, we will talk about Poisson distribution. So Poisson distribution comes from a type of experiments called Poisson experiments. So the Poisson experiments measure in a given time interval and occurrence of some kinds of event during a given interval or a specified region. And the properties of Poisson experiments is that the number of, for example, the telephone calls received per hour by an office, and the number of days schools is closed due to snow during the winter. Note that the specified region does not necessarily be a time interval. It could be generalized as a line segment, an area, a volume, or perhaps a piece of material. But most frequently we use time interval for this time period for the Poisson experiment. So the Poisson experiment is derived from the Poisson process and possess the following properties. So first, the number of outcomes occurring in one time interval or specified region of space is independent of the numbers that occur in any other disjoint time interval or region. So this is independent for a very small element of this time interval. So in this case, we can say that the Poisson process has no memory. So what have occurred before this time interval has no any effect on what has occurred after this interval, right? And the probability that a single outcome will occur during a very short time interval or in a small region is proportional to the length of the time interval or the size of region. So Poisson process, if we want to measure, for example, 10 hours, so we can use a mean value. Mean value, which means the 10-hour times a very small unit, 1 hour, has a lambda of occurrence. So this is linear. So 10 hours mean value is 10 times of 1 hour's mean value. And 100 hours mean value equals 100 times of 1 hour's mean value of occurrence. And the probability of more than one outcome will occur in such a short time interval or fall in such a small region is negligible. So this means, we assume that in Poisson process there's no possibility that two events occur exactly at the same time. This is not possible. So we occur only one occurrence after one occurrence. So not possible for the two occur exactly in one very, very, very small time interval, right? So from Poisson process, we can get Poisson random number. So what is the Poisson random number? So measure the number x of outcomes occurring during a Poisson experiment is called a Poisson random variable. And its probability distribution is called the Poisson distribution. So Poisson distribution is a discrete random variable. It measures how many times occur of such events during a time interval. So the mean number of outcomes in such a specified time interval called mu. For example, we measure 10 hours in the 10 hours occurrence. So mu is for the 10 hours average occurrence of such event. And here mu equals lambda t. So the t is 10 hours for the specified time, distance, area, or volume of interest. And the lambda is the mean rate of a unit time for 1 hour, for example, for 1 acre, right? For 1 millimeter, for 1 liter, right? And the probability distribution of Poisson random variable can be calculated as px lambda t. So x is the probability for how many times of occurrence in such a time interval, equals x factorial in the denominator and numerator the two parts multiplication. The first part is the power of e with minus lambda t. Here lambda t is also the mean value for this specified time period. Then times lambda t's x power. So for example, if x is 2, so we just fill in the 2 factorial in the denominator and the lambda t 2 power. Then times e minus lambda t power. So Poisson distribution calculation can be used from a table if you want to calculate manually. This is called Poisson cumulative probability. So what this means? So for the mu, here mu is lambda t, right? For the time interval, in the time interval, for example, mu equals 0.5. We just check r is x. For r equals 0, probability is 0.6065. Then for the 1, which means 0 plus 1 for the cumulative up to 1 is 0.9098. So if we difference between these two comes about 0.30. This means the probability for 1 is 0.30. And so on. These are for different mean value, and you can calculate each probability for individual number of r. Here r is same as x in the previous page's formula. So we take a look at an example. During a laboratory experiment, the average number of radioactive particles passing through a contact is 1 millisecond in 4. So this 4 is lambda, right? What is the probability that 6 particles enter the contact in a given millisecond? So the solution is using the Poisson distribution with x equals 6. So here we want to know the probability associated with x equals 6 and the lambda t equals 4 because we focus on 1 given millisecond. So here 1 millisecond is 4, so lambda t equals lambda times 1 equals 4. So referring from the table, we can get probability of x equals 6, mu equals 4, lambda t is 4. Then the calculation is 6 factorial in the denominator is minus 4 being power. Then 4 is power, 6 power. And this calculation can be very tedious. So you can use the table from Poisson distribution, which equals cumulative Poisson distribution up to 6 with mu equals 4 minus the cumulative distribution up to 5 with the same Poisson distribution. So the probability of occurrence with 6 is about 0.1042. So another example is 10 is the average number of oil tankers arriving each day at a certain port. The facilities at the port can handle at most 15 tankers per day. So what is the probability that on a given day, tankers have to be turned away? So the solution is, if we let x be the number of tankers arriving each day, so using the Poisson table, we can calculate the probability. In this question is the probability of x larger than 15, right? So which means this is 1 minus probability of x less than equal to 15. So this actually is 1 minus the cumulative probability of Poisson distribution with a mean equals 10, right? So the answer is 0.0487. So you can see this probability is quite low. It's a very low chance, about 1 of 21's chance that a given day tankers have to be turned away. So this is the probability distribution figure for the Poisson distribution with different mean. So mu, here mu is lambda t equals 0.1. It occurs most occurrence at the Poisson random variable is 0. And if we say mu equals 2, so most occurrence at 1 or 2, right? And 3 about. But if we let mu equals 5, can see most occurrence at 4, 5, 6, but comes very symmetric in shape. So when the Poisson distributions, lambda t mu gets large and the shape becomes more and more symmetric. So next we will see the approximation of binomial distribution by a Poisson distribution. So Poisson distribution actually can be viewed as a limiting form of the binomial distribution. So we know binomial distribution measures the success times of x in n child with the success rate for each child is a p, right? But when n is very large and p is very close to 0, so p, for example, is about 0.001, but with n 1,000 times of trial, in such experiment, so binomial distribution can be approximated with a Poisson distribution with the mu mean in a Poisson distribution equals np equals binomial's distribution's mean. So if let x be a binomial random variable with probability distribution bx and p, so n is infinitely large and p is very close to 0, so the np is constant, which means the Poisson distribution's mu is also constant. So we can use Poisson distribution to approximate a binomial distribution. So let's look at an example for this case. So at a certain industrial facility, accidents occur infrequently. It's known that the probability of an accident on any given day is 0.005. And accidents are independent of each other. So what is the probability that in any given period of 400 days, there will be an accident on one day? And the question B is, what is the probability that there are at most 3 days with an accident? The solution is, let x be a binomial random variable with n and p. N is 400 and p is 0.005, so we can get np equals 2. In this case, we can use Poisson approximation. So in first question, we can calculate the probability of x equals 1, which means is 0.271. And for the question 2, we can calculate probability of x less than or equal to 3, so which means is the cumulative probability up to 3 in a Poisson distribution with mu equals 2. So its probability is about 0.857. Thanks for watching.